We're going to finish up Unit 2, which goes pretty quickly with Lewis diagrams, resonance, formal charge, VSEPR, and bond hybridization. You're certainly going to have to put in some study time on this, but remember, when you're making up your review sheets, listing your VSEPR structures and bond angles and hybridization can be helpful in remembering that information. So the whole purpose of our chemical bonding here is to understand our electrons, how they're distributed in the molecule, and how to determine their molecular structures. So eventually we can get to bond properties and bond energies. Covalent bonding, remember, is a sharing of those valence electrons. Doesn't mean an equal sharing, but right now we're looking at just sharing electrons in that covalent bond. So you've got your core electrons, your valence electrons, and of course it's your valence electrons that are involved in this bonding. And it's really important that you can count up valence electrons in order to bond correctly. So your Lewis dot structures have your bonding pairs and your lone pairs, and you just want to be able to count up how many electrons are bonding and how many are lone and make your Lewis dot structure correctly. Remember, it's just the blueprint for your molecule. So your lone pairs or non-bonding pairs are to be represented as 2 dots, and your bonding pairs as a single line. So I think I may have told you before, you can do your lone pairs as a small dash, but I don't think on this year's exam that would be in your best interest. So show 2 dots for your lone pair and a line for your bonding pair. Your bond formation then is an overlap of those orbitals. So you get an overlap of orbitals where you're sharing those electrons, and that is called a sigma bond. So that sigma bond is the overlap of those orbitals where your electrons are bonding. This overlap creates the molecular geometry of the compound, as those atoms, those terminal atoms on the end, will want to stay as far apart from each other as possible. When you review your rules of your Lewis dot structures, you have to add up all your valence electrons, put your central atom, which is usually the first, unless the first is hydrogen, form all your single bonds, follow the octet and duet rules. Make sure when you have carbon and nitrogen and oxygen and fluorine, you always have 8 electrons, and with hydrogen, you have only 2. These elements always obey the octet and duet rules as they have only s&p orbitals available. Do not form multiple bonds unless single bonds won't work. Multiple bonds are much higher in potential energy and will not naturally form. So following those rules, you should be able to quickly draw any Lewis dot structures they give you. Remember, boron tends to form fewer than 4 bonds. It's electron deficient and usually only has 3 bonds or 6 electrons. You can start breaking the octet rule with third row elements and larger that will often satisfy the octet, but they can hold extra electrons in their d orbitals. So if you have extra electrons, if you've counted them up and you have more that you need to place, they have to go on that central atom, and it has to be able to break those rules. So you often get multiple bonds, especially around molecules that contain carbon and nitrogen and oxygen. Those are the most common, and then sulfur and phosphorus. So if you go back and look in your lab notebook, you will have drawn most of these structures. Some of them are used so commonly in the AP Chemistry exam that you really want to review those most commonly asked for molecules, and they should be in your lab notebook because you did a large lab on Lewis dot. So violating that octet rule, there has to be a reason for that. So you either have an atom that prefers to be electron deficient because of formal charge, and we'll look at boron later, or you have a central atom that can hold those extra electrons. So when you have a molecule that has a multiple bond, it is possible that you will have a resonance structure. That means that you can move that multiple bond to multiple places and still have a valid structure. When you draw those different resonance structures, you're not saying those bonds flip around. You're saying that this molecule contains some kind of an average of all those resonance structures, that it doesn't contain two single bonds and a double bond. It contains an average of that. And our bond order is going to help us to prove and support our resonance structures. Remember, a resonance structure would have only one bond length. It would be a hybrid or an average. It doesn't flip back and forth. This kind of equilibrium arrow that's typical is a little misleading. We're not saying it's flipping back and forth. We're saying it's an average. So you have a double bond and a single bond. So you actually have a 1.5 bond order. So you have an average bond that is shorter than a single and longer than a double. So it is an average of those. So you definitely do not want to think you have two different bond lengths here. Resonance questions on AP exams can be very tricky. They'll say, how many bonds types do you have? And if you don't stop and think, you're going to say, oh, well, I have one single and one double. One would be shorter and stronger than the other. Not true. You have a resonance structure with an average bond length and an average bond energy. One bond type. If you can, draw a resonance structure and it asks you to, simply move that multiple bond around to locations that it can occur. Pay attention, you couldn't move a multiple bond with a hydrogen on the end of it because hydrogen cannot have two bonding sites. So just make sure you don't make a silly mistake when you move that multiple bond. So in order to determine which is your best resonance structure, you look at formal charge. And you do that by trying to get a structure that has formal charges on its atoms as close to zero as possible. You're trying to come up with a structure where the electrons are distributed to the most stable state. So to calculate formal charge, you simply count up the number of valence electrons around the atom that you're talking with. How many electrons does it bring? Then half of the bonding electrons, so half of them belong to one atom and half to the other. So half of them belong to that carbon and the other half. So if you have a bond, you have one electron for each of the bonded, and then all of the lone pairs that belong to that atom. So you're looking to count up the number of valence and subtract half of the bonding and half of the lone. So for carbon dioxide, if we look at the oxygen here, we have, how many valence electrons do we have for oxygen? Look on your periodic table. You've got 6. Half of the bonding electrons, so the bonding electrons are these right here. So you've got 4 bonding, so that would mean half of them would be half of 4, or 2, minus the 4 non-bonding or lone electrons that all belong to oxygen. and that gives you a 0 formal charge, which is favorable. That's what you're looking for. If you move on to carbon, you'd add 4 for your valence electrons minus half of the 8 that are being shared right in here by carbon. So you've got 2, 4, 6, 8. 2 of them belong to carbon here and 2 there. So minus 4 minus 0 gives you a 0 formal charge on carbon as well. And then the other oxygen would be exactly the same because its structure is the same. So this structure gives you 0 formal charge on all of your atoms. That means it's a very good resonance structure. Let's look at a resonance structure that could have a triple and a single bond. It is possible that instead of 2 doubles, you would do a triple and a single. If we do the formal charge on that, for that oxygen, it's still going to be 6, but this time 1/2 minus 2, so 6 minus 1 minus 6 gives you a -1 on oxygen, and you want a 0. Now, a -1's not horrible for electronegative element, but it's not as stable. If we go to the other oxygen, we're going to see a 6 minus half of 6, or minus 3, minus 2, giving us a +1. Well, that's a very unfavorable charge on an electronegative element. The carbon would be exactly the same with a 0, but between these two resonance structures, you definitely will have a better resonance structure if you pick the double bonded carbon because of the formal charge being 0 on each element. So that would be all you would ever have to do to pick out the best resonance structure. You might draw them, they might draw them, and ask you to pick the best based on formal charge. And you always pick the best resonance based on formal charge. Sometimes, if you draw a Lewis dot structure following the octet rule, which we expect you to do, you will see that you do not get a structure with great formal charges. And then if you redrew it with multiple bonds, and sulfur can break the octet rule, so you could put multiple bonds. So if you redrew it with 2 multiple bonds on the sulfur, you would get a much better molecule in terms of formal charge. But it does break the octet rule. Now let's be very clear. No one expects you to draw, by breaking the octet rule, something that has better formal charge. That's just not what we want. We would want you to draw the Lewis dot structure based exactly on what you would predict for this following the octet rule. However, if you were given this structure and then given this structure, you certainly could determine that this structure based on formal charge was better. But please, please, please do not think you are expected to figure out by using multiple bonds which molecule will give you the best formal charge. Just not required at all. Boron trifluoride is electron deficient based on formal charge. So if they showed you this structure and asked you why it was the best, you could quickly figure out the formal charges. So that would give you a formal charge of +1. So if we put a double bond in there and not the single bond, which we know to exist, we would get these formal charges. And they're just not the best formal charges for a molecule. You've got a +1 on a highly electronegative element, and it's just not a great arrangement. But if we follow what we know boron does, we get nice formal charges of 0 for everything. So now we know that boron is electron deficient because of formal charge. It has a better formal charge, but breaks the octet rule. So unless you're specifically asked to pick the best resonance structure based on formal charge, you really don't need to worry. However, boron is one of those elements we expect you to know always breaks the octet rule. So bond order will help you discuss bond strength and bond length. So a single bond has a bond order of 1, a double a bond order of 2, and a triple a bond order of 3. Triple bonds are stronger and shorter than double, are stronger and shorter than single. If your molecule has only one type of bond, like F2, O2, or N2, then it's not a big deal. You say bond order of 3, and it's a triple bond, and that's a strong, short bond. But when you have more than 2 atoms in the molecule, and you have multiple bonds, to determine the bond order, you draw the Lewis dot structure and count up the total number of bonds and the total number of bonding groups, and divide the number of bonds by the total number of bonding groups. And this will give you that, because you have to have a resonance structure in order to even be thinking about bond orders being more complicated than 1, 2, or 3, it will give you that average bond that you're looking at, that we say when you're talking about a resonance molecule, you know you don't have 2 different types of bonds, you have 1 type. So let's look at an example. So we know that NO3 has 3 resonance structures. You could draw them all out. What you would do to find the bond order is to count up all of the total bonds. So you've got 1, 2, 3, 4 total bonds, and then you divide it by the 3 bonding groups that you have. So there are your 3 bonding groups. So divide the total number of bonds, 1, 2, 3, 4, by the bonding groups, and you get a bond order of 1.33. Look at the logic of this. If you were looking at this resonance structure as not having a double and 2 single, but some kind of average between it, having that double and 2 single average would lead you to a 1.33 bond order. 1.33 is shorter and stronger than a single, but not as short as strong as a double, which would have a bond order of 2. So a stronger bond, the higher the bond order, the stronger and shorter that bond is. If you have NO2 plus 1, if you look, you draw 3 resonance structures. If you were asked, you absolutely would not have, this is 1 resonance structure, and you wouldn't say that you had all the bonds exactly the same, nor would you say you had a triple and a single here. These are resonance structures. So what you would do is count up in all of them around that nitrogen. You have 4 total bonds divided by 2 bonding groups, giving you a bond order of 2. So the triple single average is a 2, and the double double average is a 2. So bond order will allow you to discuss between these 2 structures which one has the strongest bonds. And you can tell that it's the bottom one, the NO 2 with the plus 1 or plus 2 charge, excuse me, whatever, I guess it's a plus 1 charge, has a bond order of 2 that is a shorter, stronger bond than the average 1.33 bond order in the top molecule. So comparing bond strength using bond order. This is another really good example. If you're comparing NO2 and NO3, you have resonance structures for both of these, but overall, your bond strength in NO, you have a much stronger bond, a much shorter bond than you do in NO3. And you can support that with bond order. You jump from that to molecular geometry. So VSEPR theory, valence shell electron pair repulsion, you're going to put those electrons, you're going to put those atoms, and they're going to repel each other. They're attracted to the central atom, but the lone pairs on each of the terminal atoms will repel each other and give you the geometry that we know to exist. So it's based on repulsion between electron pairs on those terminal atoms. The molecules will adopt the shape that minimizes the repulsions between the terminal electrons here and here, and the attractive force here is increased. So the molecular geometry comes from balancing those forces. And you've got a cheat sheet with this. You're able to write this cheat sheet down on your notes that you're making for me on each chapter. So you've got your linear, your trigonal planar, your bent, your tetrahedral, trigonal pyramidal. All of these will come once you have a geometry. You remember you're only counting your multiple bonds as one effective pair. So this is 3 bonding sites. That would be trigonal planar. If you've got 4 bonding sites, you've got a tetrahedral. You've got 3 bonding sites and a lone pair of electrons up here. So that is going to give you a trigonal pyramidal geometry. Your water has 2 lone pairs around there. So your bond angles are affected by those lone pairs. So here, your lone pairs of electrons up here would repel more and push these bond angles closer together. And your 2 lone pairs of electrons here would repel even more and squeeze your bond angles down in water. So even though you have a tetrahedral arrangement of everything around here, if you have lone pairs, your geometry becomes trigonal, pyramidal, and bent based on your lone pair repulsions. You have structures that don't obey the octet rules when you get into your VSEPR. And again, this is a matter of memorization and having built and drawn enough of these. Remember, there's a very good link to building these molecularly. If you're still having trouble visualizing them, it's still in your folders, and I'll post it again for review. Once you've determined your molecular shape, then you determine your molecular polarity, which is going to lead you to your intermolecular forces. So molecular polarity is determined by having a dipole moment in your molecule. So you're looking for an asymmetrical molecule that has lone pairs that don't cancel each other out. So a molecule, okay, if molecules are nonpolar and symmetrical, so if you have polar bonds, so this is a polar bond, hydrogen and carbon have a difference in electronegativity, but those polar bonds are distributed symmetrically around that central atom, that molecule will be nonpolar. So you can have a nonpolar molecule that's very simple, like O2, and you have a nonpolar bond and a nonpolar molecule. But you can have polar bonds, but still have a nonpolar molecule if those bonds cancel out, if those dipoles cancel. Molecules are going to be polar if your bonds are polar. Okay. So if you have a polar bond, 2 different atoms, and you're not symmetrical, so you have a lone pair of electrons up here giving you an asymmetrical geometry, you have a polar molecule. If you have a polar molecule and you can determine that simply by saying the dipoles don't cancel, then you can answer all of your intermolecular forces questions as well. So CH4 is a symmetrical molecule. The dipoles cancel and the molecule is nonpolar. CH3F, because you have a different electronegativity in this part of the molecule, you have a partial negative and partial positive charges here. you have a non-symmetrical structure where the bond dipoles do not cancel, so the molecule is polar. Carbon dioxide is not polar, even though the bonds are polar, because of the canceling of those polarities due to the symmetry of the structure. So once you can determine polarity, that leads you to our next chapter on intermolecular forces. This is a large section right here, so it's got a lot of material in it. So the last thing we'll cover is hybridized orbitals. So there's very little that you really have to do in order to answer these questions, but let's go through the theory of this. We know that when molecules form, they don't use their atomic orbitals. It wouldn't work. You would not get the same equivalent bonds. So they hybridize. They blend their s and their p orbitals to create equivalent bonds. So the sigma bond is an overlap of orbitals. So we need to review that so when we get into pi bonds we understand. Every molecule can have only one sigma bond, only one overlap of orbitals where those two electrons are going to reside between those atoms. So if you look at methane, you have 4 carbon-hydrogen sigma bonds at 109 degrees apart. In order to get 4 equivalent bonds, we have to blend our S and our 3 P's together to make an sp3 hybridized orbital, all pointing at the 109 degree bond angle from that central atom. So anytime you have 4 bonding sites, you're blending an S and 3 P's for 4 equivalent bonds. So blend the S and 3 P's to get sp3 hybridization, gives you tetrahedral geometry. So instead of an S and 3 separate P's, we mash these guys into a hybrid orbital where you have an sp3 hybridization. So blending the S and 3 P's gives you 4 equal orbitals. Always, tetrahedral has sp3 hybridization. If you're sp3 hybridized, you do not have any multiple bonds. In terms of energy, your S is lower than your hybridized orbitals, but your P by itself, your unhybridized, if you had one later on, would be higher in energy. So the sp3 hybridization has an energy in between the S and the P. Anytime you have 4 effective pairs, 4 equal bonds, 109.5 sp3 hybridized. You also have sp3 hybridization in ammonia and water because your lone pairs of electrons are still in those orbitals. The bond angles are no longer 109.5 because you're pushing them together with your lone pairs, but your hybridization remains the same. You're still using 4 bonding sites. It's just that 2 of those bonding sites in water have lone pairs, and in ammonia, 1 of those has. So your hybridization for 4 things around the central atom doesn't matter if they're bonding or non-bonding pairs. sp2 hybridization, unless you're boron and break the octet rule, you're going to have multiple bonds. So now you're going to blend your S with 2 of your P's, hence sp2. That gives you 3 equal hybridized orbitals and 1 unhybridized or unchanged p orbital. So take the S and the 2 P's and blend them together, giving you 3 equal bonding sites, which would be 120 degrees away from each other, which is your sp2 hybridization and your trigonal planar geometry. Always, sp2, 120, trigonal planar all go together. So if you're looking at your sp 2 hybridization. Here you've got your overlap here, and you have your unhybridized P's here. This is where you can get an interaction with that unhybridized P to give you that double bond. So the hybridized sp2 is of lower energy than the unhybridized 2p. So where is that unhybridized 2p? They are always perpendicular to the sigma bond. So the sigma bond is the overlap, and then these are the unhybridized. So if you're putting your carbon and carbon together, then this double bond that you draw, that's the pi bond with those electrons above and below. So when you draw a double bond, you have sp2 hybridization. You have a trigonal planar structure. So C2H4 is going to give you your sp2 hybridization. But you don't need to go into all of this. You need to see that you've got 3 bonding sites. Well, carbon can't break the octet rule, so you have to have another bond in there. But you still have, you count this only one time for your hybridization, just like you count it for your molecular geometry, only one time. This is not shared in a different space, so you do not need to remember, even though we draw it here, it doesn't exist between those atoms. So 3 bonding sites, sp2. Just different, showing where those pi bonds are located. Your pi bonds are above and below the sigma bond. Lots of different ways to show that. Pi bonds are where you can have delocalized electrons that can move. So if you have sp2 hybridization, you do have delocalized electrons that occur in that pi bond. So 3 effective pairs, 120, trigonal planar. sp hybridization, you're blending an S with a P, leaving you with 2 unchanged P's. Go through this pretty quickly. So you blend those 2 together, you get 2 equal orbitals. They've got to be pointing in opposite directions with a 180-degree bond angle. So anytime you have sp, you're going to have a triple bond or 2 double bonds. So you're going to have 2 pi bonds and 1 sigma. Remember, you can always have only 1 sigma bond. So now you have 2 unhybridized p orbitals that are going to hold electrons. So carbon dioxide is a good example of that. If you look at the carbon, okay, it's got only 2 bonding sites, so that means it's got to have an S and a P hybridization. That means 2 unhybridized p orbitals on the carbon will bond with unhybridized p orbitals on the oxygen. So 2 bonding sites, sp hybridization. Either 2 double bonds or a triple bond. So 2 groups, 180-degree sp hybridization, 1 sigma, 2 pi. So 4 effective pairs was your sp3, 3 effective pairs was your sp2, and 2 effective pairs was your sp. So it really just boils down to that, and you should be able to answer hybridization questions. The other thing you have to be able to do is to count up your sigma and pi bonds. So going through your molecule, you would have 1, 2, 3 hydrogens. So that's 1, 2, 3, 4, 5, 6, 7, 8 9, 10, 11 sigma bonds, and then you go back and count that double bond one more time for one pi bond. So this sums up all of your molecular geometry. It's a big section, so you might want to break it down into smaller bits and pieces until you master it.